Hello, everyone. A very good evening. Thanks for tuning in on a Sunday evening. I'm Aniruddhan Ganesaraman, the coordinator of STEMS 2022. And I'm very happy to share that we are now midway through the STEMS 2022 lecture series that is being conducted in association with the Roots program of the Raising a Mathematician Foundation. I hope all of you are having as much fun in the lectures as we are. Today's super exciting session is by none other than Professor Rajesh Gopakumar, one of India's foremost theoretical physicists, and the present director of the International Center of Theoretical Sciences, that is ICTS Bangalore. He completed his MSc in physics from IIT Kanpur and went on to pursue his PhD from the Princeton University in 1997. He has then held various positions at various renowned universities, including those at Harvard, Harish Chandra Research Institute, that is HRI in Allahabad, the Institute of Advanced Studies in Princeton, etc. He's been bestowed with various awards, including the ICTP Prize, the Shanti Swarup Bhatnagar Award, the Swarna Jayanti Fellowship, the World Academy of Sciences Prize for Physical Sciences, etc. His research interests are majorly in quantum field theory and string theory, the later of which we'll hear directly from Professor Gopakumar himself. And today's lecture will expand on the short exposition we saw of string theory in the interview of Professor David Tong of the University of Cambridge about 2 weeks ago. Please do turn on your video so that we can come closer to having a live session. And if you have any questions at any point in the talk, do use the raise hand option and we'll take it up with Professor Rajesh. And I'm sure all of us are really very excited about this session. So without any further ado, over to you, Professor Rajesh.
Okay, thank you. Thank you, Aniruddhan, for that, for the invitation to speak at this forum and for your introduction. I'm very happy to see this activity and of course, very happy to support it. I think it's great that as undergraduate students, folks from CMI are very heavily involved in trying to communicate science and mathematics to an audience of students and others, potential scientists, or even lay public members who are interested in science. So keeping that in mind, I've kind of prepared a talk which the title, as you see, is about why strings. So I'm a string theorist, and perhaps many of you have heard of this term, string theory. String theory is a very ambitious attempt to understand, and that's how one often hears it, as an ambitious attempt to understand a quantum theory of gravity. But perhaps just as for people who may not have heard, may not have studied very much of string theory or related topics, you might be wondering, why strings? I mean, why do people think that string-like things might explain some of the most fundamental questions about nature? So that's what I will try to bring out, and I therefore will approach it slightly differently from how many talks on string theory do, which, as I said, usually focus on the aspect of string theory as a theory of quantum gravity. We will see how that connects to the other picture that I will try to trace out, which in some ways is kind of giving a kind of a broader historical embedding of this idea of string theory. So that's what it is. And as Aniruddhan said, please put your questions in the chat box, questions which are very immediate. Maybe in the middle, we'll have an opportunity to sort of at various breakpoints to address any immediate questions, and somewhat longer questions we can address, longer and broader questions we can address towards the end. Okay, so all right. So it's one of the very great achievements in a way of physics in the 20th century that we have been able to understand all the forces that we see around us, all the different kinds of interactions which are responsible, as we learned from Newton, for all the dynamics in the universe. It's one of the remarkable features that we have been able to understand all the different kinds of forces as manifestations of four fundamental ones. I mean, this is not obvious even when you study school physics or high school physics, because you come across, oh, there's a frictional force, there is some normal reaction, there's a elastic force in a spring. You learn all these different kinds of forces, and there's of course the forces between electrical charges, between the Earth and the Moon, and so on. But what is remarkable is that that these can all be understood in terms of four fundamental forces, of which two are very familiar, namely the gravitational force and the electromagnetic force, and in a way were known before the 20th century itself. But in the 20th century, in the 20th century, we have learned about two new forces. One is, which I will come to later, the strong interaction of the nuclear force, and the next is the weak interaction, which is responsible for radioactivity, which I won't really touch upon in this talk. But in some ways, it's sort of not very different in its ultimate framework from that of the electromagnetic, and in fact, it is unified with the electromagnetic force, and it's in a way a close cousin of the strong interactions. So there are fascinating stories of how we deciphered the nature of these forces, understood that these four forces are sort of ultimately responsible for all the interactions that we see. And secondly, how they manifest themselves in our everyday life in terms of other forces which we kind of normally talk about, like, as I said, the frictional force or the force in a spring and so on. But ultimately, all of these, and mostly it is a manifestation actually of the electromagnetic force, many of the other forces. And of course, there's gravity, which we know of. These two forces, and this is why they were not discovered before the 20th century, they appear only when you go into at the atomic level. But there are fascinating stories here, which I will only probably be able to touch upon. The main thrust of my talk will be what I said in the beginning, why strings, the notion of strings, very naturally arise in these descriptions of these forces. So that's going to be the central theme of this talk. So let's start with gravity. As I said, it's the most apparent force in nature. And in fact, Newton's law of gravitation, which many of you would have probably studied definitely in high school. If you are in high school, you would have come across Newton's law of gravity, which was in a sense the first universal law in physics, proposed by Newton to apply not only on Earth, but everywhere, in some sense, at least, to the known universe in his time and beyond. And this is the famous law, and which is the inverse square law about the gravitational force falling off with the distance in an inverse square proportion, and being directly proportional to the masses of the two objects. And this is what describes gravity on Earth as well as in the solar system, and very accurately too. And this was the triumph of Newtonian mechanics and Newton's description of the world as we knew it, and the beginning of physics in some sense, quantitative physics. But what we have learned, and especially in the 20th century, was that as we go to the larger cosmos, Newton's law is only approximately true. And this is the story for another talk about how Newton's law came to be superseded by Einstein's theory, whereby gravity is the gravitational force was encoded by Einstein into the very geometry of space-time. I'll touch upon this towards the end of the talk, but this is, in a sense, a whole talk in itself. But at the moment, we'll leave gravity behind. I mean, I just want you to keep these facts in mind. And I want to proceed and spend a little time on this other force, which is also something many of us, when you pick up a magnet and so on, you start experiencing the force of electromagnetism. And in fact, as I said earlier, electromagnetism is the real interaction which is responsible for most of the complex arrangements of nature that we see around us. It's the reason why solids hold together into crystals, or otherwise liquids have intermolecular attraction, and so on and so forth. So most of the things, in fact, the normal reaction that you learn, which or the reason why we don't fall through the earth, is in a sense because of the electromagnetic repulsion between the atoms in our legs and that of the floor. So these so most of the forces in some way or the other that we encounter are coming from electromagnetism. And this is why the study of complex systems is so rich, because the same underlying electromagnetic force between positive, negative charges can give rise to a bewildering array of phases of matter and their properties and so on. But here we want to not so much concentrate on these complex manifestations, but look at the underlying structure of the force. So one of the great triumphs of the theory of electromagnetism was that it unified these seemingly different forces, namely the electric forces, which you see as static electricity or as lightning and around you when lightning strikes. And that seems at first sight so different from that of a bar magnet. But this was the triumph of electromagnetic theory, that it unified these. And it's a whole body of work which many of you have probably studied, even if you're in high school, about the Ampere's law and various investigations. But majorly, it's the ideas of Faraday and Maxwell that really brought these two forces together. And the culmination was in the so-called Maxwell Equations, which were written down around the 1860s. And one of the great triumphs of Maxwell, which was why it was in a sense very remarkable, this unification, was that even the phenomenon of light, which was seemingly very different from electricity and magnetism itself, the phenomenon of light was also understood as waves of electromagnetic fields, the electromagnetic waves, and these could be created by accelerated charges, like a oscillating dipole and so on. And this was demonstrated in a series of experiments by Hertz again in the 1880s, and really cemented the status of Maxwell's equations as the underlying description of electromagnetism. What I want to actually bring out over here is that there were actually two pictures of classical electromagnetism. In some ways, they are kind of associated with Maxwell and Faraday, but that's actually a bit of a simplification, but let me start there. As you know, on the right-hand side, I've tried to draw Faraday's picture. I mean, the picture, there's of course the picture of Faraday, but there's also the picture that Faraday drew in some ways. Namely, he tried to visualize electromagnetism in terms of the lines of force. And this is a very visual and very immediate way to understand electromagnetism, because this is what you see when you sprinkle some iron filings near a magnet, that they kind of arrange themselves in these patterns which kind of follow these lines of force. And Faraday tried to understand, wanted to understand the whole of electromagnetism in this language of these lines of force. And but that's not quite the version of electromagnetism we learn today in school or college. Those are in terms of these quantities which are slightly more abstract and removed from immediate experience, namely these fields, these electric field and a magnetic field, which is the idea that there is a localized at every point in space and time. So X vector represents space and T represents time. And at every point, there is a vector corresponding to an electric field, which shows locally the direction in which the electrical force acts. And similarly, the magnetic field is also another vector at every point in space and time and shows how the magnetic field acts. Maxwell wrote his equations in terms of these field-like quantities. So I wanted to contrast this and keep this in mind as we go ahead in our description of forces, that it's a contrast between these localized point-like fields. These are very localized, right? I mean, you talk about these fields at a given point, and you associate some vector at each point, whereas these are more extended objects, these lines of flux, and they are kind of a little more diffuse, but they are extended quantities which sort of know more about the global properties of the force. So though I've kind of contrasted this as sort of Maxwell versus Faraday, it's actually more complicated, the history. In fact, Faraday's pictures of the lines of flux was actually very important for Maxwell in his development of the theory of electromagnetism. He, in a series of papers starting with in 1855, I think, he started trying to write down equations for these lines of force. And he tried to model them as sort of tubes carrying some kind of fluid. So they are kind of what you would now call vortex tubes. They're kind of little spinning tubes which have of fluid. So he was guided by this analogy of fluid dynamics, that perhaps you should think of these lines of force as some kind of little tubes, and you want to try to write equations for these tubes and their motion. And he tried this for a very long time and didn't get very far until he realized that it's probably best to talk in terms of these fields that we just mentioned, these electric and magnetic fields. So finally, he succeeded in writing down these famous Maxwell equations, what are now called Maxwell equations, which govern these electric fields, magnetic fields, and the relation between them. So if you haven't seen these equations, never mind. They are sometimes taught in high school and definitely in first year of college. So this is the so-called Gauss law, which tells you about the electric field being the source for the charge, being sourced by the charged electrically charged matter. The rho is the charge density here, and this is the corresponding law for magnetism, and says that why there are no magnetic monopoles, and which as far as we know is true. And there are the other Maxwell equations which really govern how the electric and magnetic fields interplay with each other. And as they say, the cliche is, of course, the rest is history, but these equations, in some sense, I would like to say the rest is modernity, because these equations are the foundation of everything modern, so to say, in that we have, because electricity and our ability to harness electricity through the electromagnetic forces, the Faraday's equations, the Maxwell's equations, which tell you how generators work and so on. And those are the things that power everything around us today, and has, in a sense, transformed society from the 19th century to the 20th century. So these equations, in some sense, are perhaps in a sense, perhaps after Newton's equations, the most impactful equations we've had, at least till the 20th century. So, so this was, of course, a great triumph, but very soon, at the same time, around a little after after Maxwell's developments, people also realized from chemistry that all matter is ultimately made of these distinct atoms, and in the early 20th century, you realize that these are stable particles which have a substructure, namely they have a nucleus and they have electrons going around them, and these electrons carry electrical charge, they're negative charge, and the nucleus carries positive charge. But then people immediately encountered a challenge in trying to reconcile this with Maxwell's equations, because as I mentioned, when there are accelerating charged particles, they radiate electromagnetic waves or light or whatever other wavelengths of electromagnetic radiation. So people immediately got puzzled. Why don't the electrons radiate and lose energy and just fall into the nucleus? Why is an atom stable in the first place? And this was a puzzle that classical physics couldn't address. And at the same time, there were other indications about light itself, that light, which we just talked about as electromagnetic waves, actually sometimes exhibits a particle-like nature in things like the photoelectric effect, as deciphered by Einstein. And this notion that this particle-like nature of light was associated with the term photon. And so there were these puzzles that even though we thought we understood electromagnetism very well, there were these puzzles with respect to the wave and particle-like nature of light and how these charged particles in the atoms could ever be stable and so on. And this is what so this is a little cartoon which kind of I find very amusing, because it sort of captures this wave-particle duality. You see here it says light is a particle, if you see it Particle, but if you look at it another way, it's light is a wave. And that's the wave and that's the particle, and you can't see one, you can only see one or the other at a given time. You can either read it as particle or you can read it as wave. You can't do it simultaneously. You can just shuffle between the two perceptions. So in a way, I think it captures the wave particle duality of nature in a nice way. And so these puzzles could only be reconciled by the development of quantum mechanics, which is yet another wonderful story, and which I don't have time to go into in any detail here, except to just say that quantum mechanics gives a very consistent description of both light in its wave and particle-like character, but also for electrons and protons and other particles, also as waves. Things that we thought of as particles have also a wave-like nature, just like things we thought of as waves, namely light, have a particle-like nature. So, so this sort of dual aspect of all the particles and waves that one saw around us were sort of put together in a consistent way by quantum mechanics. And by 1925, this theory had been developed and was enormously successful in telling us properties of atoms and so on. So shortly after that, people realized that and it's not just quantum mechanics. You really need to apply the quantum framework to fields, because after all, something like Maxwell's equations, the underlying quantities are electric and magnetic fields. After all, light is just a disturbance in the electromagnetic field. It is waves of electric field and magnetic field. So this brought out brought out the framework called quantum field theory, which is in some sense one of the most successful frameworks we have in the 20th century to describe most of physics. It is the natural way in which waves and particles are unified, because you have these fields have both oscillations, which can go wave-like, and those are like the electromagnetic waves and so on. But you can also have localized excitations, and this little movie over here is sort of showing how fields in the quantum world, they kind of oscillate, and you can create these sort of virtual particles. And I actually especially wanted to show this movie because I think it was referred to by David Tong in his talk a couple of weeks ago as these simulations you can find on the internet. And this gives a sort of a these are actual computer simulations based on the actual equations of quantum field theory, in fact, of a particular quantum field theory that we will be talking about later. But this whole general framework of quantum mechanics is the powerful one that in some sense subsumes the ordinary quantum mechanics that you might learn in your introductory course to quantum mechanics. The quantum field theory is sort of the full overarching framework that really puts together waves and particles on the same footing. And this is by now not only the framework that describes the fundamental interactions, most of the fundamental interactions, as we will discuss soon, but also it's such a versatile and rich framework. It applies in condensed matter physics, and modern condensed matter physics really uses many of the remarkable features of this properties of this framework of quantum field theory. It's applied in statistical mechanics. It's applied in even in fluid dynamics, which all seem very far from the framework of, then don't seem like quantum systems, but nevertheless, the mathematics of quantum field theory is very flexible and can be applied to a number of contexts whenever there are these fluctuations, and these might be quantum fluctuations or thermal fluctuations. And so this is why this is a very powerful framework, and that's sort of the message I wanted to get across. But coming back to our historical development, so where quantum field theory was first developed was in applying it to the theory of electromagnetism, namely of electrons, for instance, in an atom interacting with light. And this theory was the first quantum field theory to be explored in depth, because people wanted to understand what is it that Maxwell's equations and the Maxwell theory looks like at the quantum level. And this took a while to understand due to many subtleties in understanding the application of quantum mechanics to continuous objects like fields, as opposed to just particles or waves, particles or photons. So this theory was called QED. This is quantum electrodynamics, and was the culmination of a lot of work in the 1930s and 40s, which led finally the work of Tomonaga, Schwinger, Feynman, and Dyson, led to a complete theory of electrons and electromagnetic interaction at the quantum level. And in some ways, the predictions from this theory are, I would say, they are something, if you have not seen this before, you should really marvel at the sort of the triumph of the scientific method in this theory, where this is a quantity which those who know, this is the so-called anomalous magnetic dipole moment of the electron. And this is what the theory, current state-of-the-art theory predicts, is able to calculate it up to whatever, 14 decimal places or something. And it agrees up to like 13 within the error bars. These things in brackets are the errors to which we know it. And it agrees more essentially to this 13 or 14 decimal places with experiments, very high precision experiments. So both, you see, you are really, to get this level of experimental accuracy and this level of theoretical accuracy, and to see this remarkable agreement, I think it never fails to sort of amaze me. It's something, I mean, when people tell you about science, science is not just talk. It's you get these numbers and you get these sort of remarkable agreement of a theoretical framework developed using mathematics and mathematical techniques and physical insights, and you get them to agree with things you can actually measure in the lab or in the cosmos, in this case in the lab. So that's about the QED and the triumph of QED. So one reason for this enormous success of QED, the fact that you could calculate to such high precision and so on, and why Maxwell's equations are largely right. And when, in fact, electrical engineers don't study QED, they work with Maxwell's equations, and that's good enough for all the electrical circuits and electrical gadgets that we mostly work with. That's because in some sense, the strength of the interactions are quite small. In a dimensionless sense, you can measure the strength between the strength of the electromagnetic interaction, which is proportional to the E squared, the basic charge of the electron, and in dimensionless units in terms of the Planck's constant and the speed of light. It's actually a number which is very curiously very close to a rational number, approximately 1/137 at long distances. So this receives corrections as you go to shorter distances, but this is the leading strength of interactions. And this is a small number. It's small compared to order 1. It's just 1/100. And the way, in fact, some of the things that were calculated in the previous slide is in doing a perturbative expansion in powers of this small quantity. In any case, the bottom line I want you to take away is that the quantum effects in this theory, because the strength of interaction is small, that in a way translates into the strength of the quantum effects. And while they are very important for something like the stability of the atom, in most macroscopic context, they are quite small, and the classical description in terms of these electric and magnetic fields that Maxwell had, these are very good, an excellent first approximation, and you need corrections due to quantum electrodynamics only when you go to the atomic scales. But at the same time, because of the same reason that the strength of the interactions are small and quantum effects are small, in some sense that ultimately, and maybe this you just have to take it on faith at this stage from me, that this is the reason that the lines of flux the lines of flux are very floppy and they kind of spread out all over space, and it's very difficult to describe their dynamics mathematically. And I mentioned to you Maxwell's attempts to think of them in terms of these tubes of fluid. So it's very difficult to quantitatively describe the dynamics of electromagnetism in terms of these lines of flux, these Faraday's lines of flux. And in some sense, the ultimate reason is because that in some ways, the strength of the interactions is very small. So the lines of flux are kind of very loosely kind of tied to each other. But now let me bring in the one of the more hidden interactions, the third one on my list, the strong interactions, which of course got uncovered because when one uncovered this atomic structure, one realized there was a nucleus, and this nucleus was positively charged. It comprised of protons and neutrons. But you needed a force to hold the nucleus together, right? Because the protons and neutrons, the neutrons are not electrically charged, but the protons are, and if they had only electromagnetism, they would kind of fly apart because of the repulsion of like charges. So you wanted to understand what holds the nucleus together, and there you need a new force. But maybe I should have actually, before I start on the story of the strong interactions, maybe I should pause for a moment and ask if there are any questions, immediate questions that the moderators would like to relate to me.
So far the chat has been engaging. And any questions, do feel free to raise your hand. Advait, anything?
Yeah, I see 2 interesting questions in the chat which are, I think, relevant.
Yes.
One of the questions is there any reason why the strength of interaction between charged particles is so close to the fine structure constant?
Oh, it is the fine structure constant. I didn't use that term, but what I wrote over here is what is called the fine structure constant, and that is ultimately the dimensionless number that characterizes the strength of the electromagnetic interaction. So the fine structure constant is just a name for this quantity, but as you see, it's proportional to E square, and E square is the strength of the attraction or repulsion between two charge particles of having this fundamental charge E. And you mentioned there's another question.
Yes, the second question was, how are we estimating the strength of interaction to be E squared by L?
Yeah, so as I said, E square you can understand because that's what is the strength of the charges. So in nature, electrical charges are always come in units of essentially the fundamental charge, that is the electron charge. The proton has charge +1 in those units, and electron has charge -1 in those units. Now there might be quarks which have fractional charges like 1/3 and 2/3, but normally you don't see them in sort of they are kind of confined, as I will say later. But the basic unit is therefore the electric charge of the electron, and this is so E square measures that, and then to get a dimensionless ratio, and you actually encounter this whenever you do any calculation in quantum electrodynamics, the dimensionless ratio that sort of captures the strength of the interactions is so just from purely dimensional grounds, once you have E square, you're forced to have this factor of H bar C there. So that's what determines this. And this is what appears in, let's say, the Bohr model or any calculation involving the interaction of light with charged matter.
Hello, am I audible?
Yeah.
Yeah. Is the strength of the interaction analogous to the electrostatic forces in any kind of way, formula-wise?
Yeah, in some sense it is. The electrostatic force is a particular limit of the electromagnetic force, but the electromagnetic forces have more because this is the purely static configuration. You have a force which you normally call Coulomb's law, which is E squared divided by R. So in a way, this, if you wish, is the basic strength of the interaction, because the natural length scale that appears is related to the kind of Compton wavelength. And if you write that in terms of dimensionless coordinates, you get E square over H bar C. So there is a sense in which you can translate that strength of that force into this Newton, this fine structure constant.
Okay, thank you.
Yeah. Okay, so maybe other questions we can take up towards the end. So let me, as I said, bring in now this interaction which is forced upon us when you realize that the nucleus is built out of these positively charged protons. So you need something that holds that nucleus together. And we now understand this force. Again, it took a while till the 1970s for us to understand it. And this force we now know is really to be thought of in terms of acting on the quarks, which are the constituents of protons and neutrons. So we now know that each proton is made out of three different quarks, neutrons similarly another three quarks, and it's the interaction between the quarks which manifests itself as the nuclear force, and this is much stronger than electromagnetism. It has to be, because, as I said, you want to hold the nucleus together and overcome the electromagnetic repulsion that would normally be there between the protons. So it has to be much stronger. And in fact, the nuclear force, the nuclei are very tightly bound to each other, which is why you generate so much energy from nuclear fission or nuclear fusion, etc. So the nuclear force is very strong, and if you think of it in terms of the underlying quarks, we now understand that this force actually grows with separation, unlike the electrostatic force that just came up, which dies off in a inverse square law like Newton's law, but here the Coulomb law. So unlike these forces which sort of die off with distance, this actually grows with distance, and in some ways it's like a linear potential or a constant force that operates between the quarks. And this leads to a very remarkable feature for these quarks, that they're kind of permanently confined inside. They're kind of trapped inside that proton. They can't escape because the potential is in some sense growing so that they can't overcome that. And if you put in too much energy, it will just split it into other particles, which are also bound states of these quarks. So quarks always appear, quarks and antiquarks, etc., they always appear in bound states of a particular kind. They are tightly tied to each other because of this confining force and this much stronger kind of force that acts between them. And this force can also be viewed in terms of some lines of flux of the underlying sort of field of the strong interactions. But the difference from the electromagnetic interaction is that, unlike in the Faraday picture that I showed some time ago, the lines of flux are actually bundled up into really a string-like tube. So remind you that earlier Maxwell tried to view things in terms of these tubes or these vortices, this lines of flux, but wasn't a very good approximation because the lines of flux kind of spread out all over, and you can feel the electromagnetic force very far away. But like I said, the strong interactions operate within the nuclear length scales, and that's because the lines of flux are now not able to spread out. The nature of the underlying force, which I'll just mention, the nature of the underlying interactions is somewhat different from the Maxwell theory, and it's a generalization of the Maxwell's theory, which has the remarkable feature that the lines of flux are now kind of cannot escape, and they're kind of bundled up into a tube between, let's say, a quark and an anti-quark. They're kind of in some kind of a tube between them. And there is this is a picture again from the same person's simulations about the quarks. And you can see in this case, they're kind of oscillating, they're kind of trapped and they're oscillating. And there's these lines of flux are between them, kind of elongating and coming together. So this is the sort of flux tube. And this is sort of a real effect that is there in these theories. It is something very similar to another effect that may be somewhat more familiar to some of you in the audience who may have heard of this thing called the Meissner effect in superconductors, where magnetic lines of flux cannot penetrate usually a superconductor, but when you increase the magnetic field high enough, they do penetrate in little tubes, in these little vortex tubes, and which are called superconducting vortices. And the magnetic field can penetrate, but they are kind of completely these lines of very narrow lines of flux. So in some sense, you see a similar phenomenon even in Maxwell's theory, but in a more unfamiliar context like superconductivity. You don't see it in normal magnetic fields or electromagnetic fields, but you can see a similar phenomenon in even in electromagnetism, but when you are in a superconducting medium. So what is this force of the strong interactions that gives rise to this sort of very interesting behavior? This is a beautiful generalization of Maxwell's theory, which was developed in the 1950s. It's called the Yang-Mills theory, or the Yang-Mills quantum field theory. So it's also a quantum field theory, but generalizes the Maxwell's QED theory, the quantum electrodynamics theory. It's a more complicated theory involving more complicated interactions between the fields, which is what gives rise to these properties, this property over here of this flux tube being confined in this tube. And this theory was sort of finally developed by the mid-70s and is called the quantum is now called QCD, or quantum chromodynamics, as opposed to quantum electrodynamics, where the chromodynamics refers to the underlying force between the quarks is sometimes called a color force because of various historical reasons, and due to the sort of fact that the Yang-Mills theory can be, these Yang-Mills theories can be viewed as a theory of not just a single charge, but a sort of a more complex color charge. So that's the reason for the term quantum chromodynamics. But anyhow, just treat it as a name. So QCD is the modern theory of the strong interaction, and it has this feature that the flux lines over there are also in this very behave like some kind of a string-like object. So actually, even before the strong interactions and this feature that was discovered was uncovered, before people understood this phenomenon of this confinement or this string-like flux tube, the legendary physicist Paul Dirac, one of the founders of quantum mechanics in the 1920s, he thought a lot about electromagnetism itself and at the quantum level. And I just wanted to share a quote of his from 1950s, mid-50s. Actually, he gave a series of lectures at the Tata Institute in Mumbai in 1955 or so, and said very similar things. This is a quote a little bit afterwards. And I just want you to this thing that he was trying to create a model, as he says, in which the basic entity is the line of force, a thing which is like a string instead of a particle. And it is these strings which will move about and interact with one another according to quantum laws. I think this was a very prescient statement. And in some ways, he used this word strings. And this was before anything like string theory had been even contemplated or discovered or whatever. So he had this, he always wanted to reformulate quantum electrodynamics, again, like Maxwell, sort of going back to Maxwell's idea, but now in the quantum level, that maybe now we can kind of think of the line of force as the basic entity, and which is more like a string-like object, and try to describe in terms of these strings, describe the dynamics in terms of these strings rather than focus on the original particles or fields. So this was Dirac. And in some ways, the picture that I showed in the previous transparency was sort of showing how these lines of flux actually really become very real in the case not immediately of electrodynamics, unless you count the Meissner effect and superconductors, but in the context of the strong interactions, in the context of QCD, the kind of simulations that I was showing you earlier. So this is sort of what, in some ways, brings now, so these Yang-Mills theories help to bring strings in focus, so to say, because as I said, firstly, these lines of flux are very natural things to consider in these theories, which are very different from electrodynamics. The underlying quarks are always confined because of this linear potential they are in. And they are also, another reason is that these theories are intrinsically very strongly interacting. The corresponding dimensionless quantity, which characterized the weak the electromagnetic interactions, and which was 1/137, this fine structure constant. The analogous thing in these Yang-Mills theory is of order 1. So it's not, there's no sense in which the quantum effects or the interactions are small. They're always very strong. And so it's in a sense, a highly quantum theory, which is, of course, why you don't see the strong interactions at the classical level. You don't see them in beyond the nucleus size usually. So the techniques for dealing with theories which worked in the case of QED, which was relying often on the fact that that fine structure constant was very small, those techniques no longer apply. And so these are really strongly interacting theories. And this is why the Faraday lines of flux picture is potentially very useful, because maybe now you don't need to think in terms of the field picture. The field picture is perhaps not so useful. You could try to write equations which are directly for the dynamics of these string-like objects, like Dirac or even earlier Maxwell hoped to write. But now these are very concrete flux tubes that we have in the Yang-Mills theories, and we can try to find equations for the dynamics of these strings. And so people were very enthused by this and tried to do that. And in fact, quite remarkably, if you just try to look at a sort of a free string, which is a string-like object, which is moving in a relativistic way. So you have to, of course, take into account not the kind of strings you study in a violin or a skipping rope or whatever. You consider kind of a relativistic analog of that. But those kind of strings also have excitations, very much like a violin string. They or a sitar string, I mean, they will have harmonics. And these, if you consider a string of that kind and look at its excitations, these harmonics, you find that the energies of these, or the masses of the excitations that you get of the string, are very close to those of the so-called mesons, which are bound states of a quark and an antiquark, like the ones that I showed, which are connected by the flux tube. So the different excitations of that picture, that movie that was playing earlier, this different excitations do seem to capture the energies of the different particles that you see, the mesons, which you can't calculate using which are difficult to calculate using the field picture. But there was a catch in that many other detailed properties of the quantum chromodynamics seem to disagree with this sort of simple string picture. And this was kind of, and I mean, these are sort of more detailed properties. And in some sense, this has to do with the fact that the string that appears in the QCD, in the strong interactions, is something like a fat string. As you saw in that movie or the picture that I draw, it has a certain thickness, and that thickness is related to the so-called tension of the string. This thickness is very different from the kind of if you want to try to capture that thickness of the string, that's very different from the kind of framework that you normally would use to describe just the simplest framework to describe the motion of strings would think of them as idealized, namely thin strings, which, just like when you study Euclidean geometry, you think of points as with no extent and lines as things which have just an extent but no thickness. Similarly, in quantum fields is the theory which describes point-like particles, and corresponding string theory is simplest to describe in terms of these idealized thin strings. And so it seemed like while these idealized thin strings seem to get some things right, namely like the set of these bound states that I mentioned, which are harmonics, but the detailed properties of the interactions and so on were kind of different. So there was a bit of an impasse, and people didn't really know whether, well, I mean, then how do you how do you try to write down the equations for these strings and see whether QCD can be described by a string theory? And this is where I'm sort of jumping in a historical sense, where in the turn of the previous century, new insights actually suggest that the QCD-like strings are objects that do obey equations of idealized strings, except that they are not the equations of the strings moving in the four-dimensional spacetime that we would naturally assume they are in. Their equations are like those in a curved spacetime in 5 dimensions, a particular curved spacetime called anti-de Sitter spacetime. And the picture is something like this, that you should think of this square over here as our 4-dimensional spacetime, the 3 space and 1 time direction. And then there's an extra 5th direction, and this direction is a kind of a more curved spacetime direction. And the whole geometry, this 5-dimensional geometry, is a sort of hyperbolic geometry or anti-de Sitter spacetime geometry. And the idea is that there is a idealized thin string in this 5D whose shadow on the 4 dimensions is like this fat string, this flux tube. So that flux tube is a bit of a shadow of an idealized string. As you can imagine, when you kind of project a very thin object onto a screen, it'll tend to have a thickness. It'll sort of smear out. And that's what this effect is capturing. And so this seems like a bizarre picture, very but in the 24 years since this insight of this Argentinian physicist Juan Maldacena, we have realized more and more situations where this is true, and we have very strong reason to believe that this picture is indeed correct, even though we haven't fully understood it for QCD. But for many QCD-like theories, very similar theories, cousins of QCD, there is such a picture very concretely. You can realize, you can understand it and talk about the equations of this 5-dimensional string in this curved space, which sort of describes, when you project it as a hologram, it describes this this flux tube. So that seems to be the resolution of that impasse. But this means that I should bring in finally gravity, and I know I'm reaching the 1 hour mark, but I think I should be done in 5-10 minutes. So because I talked about curved space-time, and this is where the gravitational force enters, because and I don't have the time to describe this in more detail. As I said, the whole story of gravitation is a remarkable one in itself, and it culminated in these equations that Einstein wrote, and you can see him on the blackboard there in the right corner, writing down the simplest version of his equations. And he was inspired by Maxwell, and it's a generalization of his equations now for describing curved geometry, and which you describe in terms of something called the metric field, which generalizes the electric and magnetic fields. And he wrote down equations which are very complex generalizations of Maxwell's equations, but it's still a classical description, so to say, like Maxwell's description. No quantum effects enter. It's a description which is supersedes the Newton's description, but is nevertheless still a classical description. And this has been very successful, of course, but we know that ultimately you need to have a quantum description, just like we had for Maxwell's theory. There are many puzzles, somewhat like the puzzles you had for atoms. There are many puzzles relating to black holes now, which come from trying to reconcile Einstein's theory in these very extreme circumstances, and you have many indications that unless you sort of treat Einstein's theory at the quantum level, you will get you will not have a complete description, just like Maxwell's equations couldn't by themselves describe atoms, and you needed to combine them with quantum mechanics to get the QED to describe them consistently. But if you try to use this very powerful framework of quantum field theory to this field for the space-time, the metric field, and you try to quantize the analog of the photon, namely the graviton, this leads to certain untamable infinities when you consider interactions. And somehow usual quantum field theory, which seemed to work very well with the electromagnetic interactions, as I described, and also with the strong interactions, QCD, and even for the weak interactions, which I didn't talk about. Even though it works so well for these other 3 interactions, it doesn't seem to work as well for the gravitational interaction. And this is where the conventional narrative of string theory normally begins, that when people studied amongst the excitations of this relativistic string in the hope of understanding QCD, when they studied this in the 70s, they realized that they could find amongst the excitations a graviton, and that when you consider its interactions in the framework of the string theory, these idealized string theories, thin strings, the interactions are perfectly finite. There are none of these untamable infinities. So this is what led to a lot of excitement for string theory as a theory of quantum gravity. There are well-defined rules for the interactions of these strings, which generalize the so-called Feynman diagrams of quantum field theory. And now, instead of point-like particles interacting, and that's what Feynman diagrams are, you have these string-like objects which kind of sweep out two-dimensional surfaces instead of one-dimensional world lines. You have sort of two-dimensional world sheets of these strings. But just to say that there's a well-defined framework for understanding the interactions of the strings, and you don't get any of these untamable infinities that quantum field theories, which are based on sort of a point-like description of gravity, normally give you. So this did seem like the right framework for a quantum theory of gravity. And what I want to emphasize is that you see the string-like objects arise naturally, not only in Yang-Mills theory and electrodynamics and these other forces, but also in Einstein's theory. I mean, Einstein's theory seems to very naturally come out of the description of these idealized thin strings. And and to make sense of Einstein's theory at the quantum level, it seems like you really need to consider these string-like objects. So strings are not some fanciful, just someone thought up one day saying, yeah, well, I'm bored of looking at particles, let's look at strings. And then why not membranes and so on. And but no, there's actually very good physical reasons to think of these string-like objects. And in some sense, that goes back to Maxwell and Faraday, and you really start seeing it in Yang-Mills theory and Einstein's theory. And it's this, and what I wanted to just mention in terms of as we close, is that the same framework captures both kinds of strings. The same framework of idealized thin strings, we now know captures not only gravity, through the sort of what I just briefly mentioned in the last slide, but also the strings of Yang-Mills theory through this holographic picture. And that was the central insight of this ADS CFT correspondence of 97-98, this holographic correspondence that I mentioned, that namely the equations governing Faraday flux tubes in four-dimensional Yang-Mills theories seem to be the string equations in 5 dimensions, which actually in some limits are in fact just Einstein's equations. So there's a very remarkable connection between Einstein's equations, that means the theories of gravity in 5 dimensions, and Yang-Mills like theories in 4 dimensions, in one lower dimension. And in some ways this can be viewed that you can describe now as quantum gravity or quantum spacetimes, at least in these anti-de Sitter spacetimes, in terms of quantum field theories, but in one lower dimension, namely this is the notion of this hologram, that boundary quantum field theory captures the geometry of the quantum spacetime in one higher dimensions. And in fact, this explains many of the puzzles of Bekenstein and Hawking on black hole entropy, etc. But that's the subject of another talk. I just want to close by just saying that this is a picture that's still being unraveled. And this is another depiction of the same thing, where you sort of have a hologram, this one lower dimensional. You can think of this as capturing that 4-dimensional hologram, is capturing this higher dimensional quantum spacetime. And but this hologram here is in terms of regular conventional quantum field theory, which you can think of as essentially lots of quantum bits interacting with each other. And that's somehow encoded in that is the notion of the space-time in one higher dimension. So in this picture, the space-time at the quantum level seems to emerge from more fundamental quantum bits on this hologram. And there are these may not make very much sense right now, but I just wanted to say that there are very fascinating ideas out there which are still being fleshed out. So you should still take them with a grain of salt, but they are very provocative ideas, which I think contain a kernel of truth, namely about how the quantum entanglement of this in this hologram, in this boundary Yang-Mills theory, kind of captures the geometry of the space-time in the one higher dimension, or vice versa. Einstein's equations perhaps are a way of geometrizing the flow of quantum information on the boundary theory. So you learn something, you can try to use, these are two very different looking descriptions, one in terms of the hologram, the lower dimensional theory, which is described in terms of a conventional quantum field theory like a Yang-Mills theory, and the one higher dimensional gravitational or quantum space-time theory. You can learn, you can use one viewpoint to say some remarkable things about the other. And that's what is happening, and many of these ideas actually are involving things at the cutting edge of quantum information and computing, as I mentioned, because you're learning something about the flow of quantum information and quantum entanglement, the structure of quantum entanglement, and that's somehow giving rise to this quantum spacetime. So never mind if this last couple of slides were very sort of impressionistic. Let me just conclude by saying, and it's not really a conclusion, it's more like a continuation of a long story, which is still not, we are not at the end of. The whole lineage of strings goes back to the flux lines of Maxwell and Faraday, and they act as an alternative to the field description, which was very successful in the case of electrodynamics, but not so successful for Yang-Mills theories. And they seem to be they are probably a much more useful alternate description. And the equations for these strings, we now seem to realize they seem to be higher dimensional, and therefore related to a higher dimensional curved spacetime, like I was saying. And so this connects with also the strings describing quantum gravity at the quantum level. So the strings describing Yang-Mills theory and the strings describing gravity in some sense are the same, and they're coming together. And this is just very fascinating. And so all this seems to hint at very remarkable things about quantum gravity, which I didn't have really time to flesh out, but it's a sort of a holographic and an emergent picture of quantum spacetime. So thanks very much, and sorry for going over time, but maybe I can take some questions.
I think to start out with, thanks very much for like the lovely exposition you gave. I think like, so chat, the people are enjoying, and it was really a fantastically structured session. And I'm sure there are like plenty of questions which Professor Rajesh has made you think of. And so maybe we'll just start with some of them. So Archis, could you unmute and ask?
Thank you, sir, for the amazing lecture. My question was, are there phenomena that string theory predicts that have not yet been observed, or some other kind of experiment by which we can verify that string theory is the reality?
Yes, no, that's a very pressing question, and something that exercises a lot of people in the field, because unfortunately, in the realm of quantum gravity, to be able to probe quantum gravitational effects, we seem to be very far away, because these appear in only very extreme circumstances, like at the Big Bang, or very much in the interiors of black holes, which you can't probe. So our only hope of seeing some signatures of direct signatures of quantum gravity seem to be in early cosmology. And perhaps one might see things there if we are lucky, but there's no guarantee, because these effects are very small. And though they are magnified by something called inflation, but nevertheless, their effects, as I said, we might be lucky and we might see signatures, but we don't know yet. But that's a potential venue where you might see signatures predicted ultimately from string theory as a theory of quantum gravity. The other place where I feel more that we are perhaps likely to realize more about string theory is in the way I described in this talk, namely as an alternative description to Yang-Mills theories, an alternative to the quantum field theory describing Yang-Mills theories, and therefore being used to describe things like QCD, or many of the similar theories that are even used in condensed matter physics. Modern day condensed matter physics uses very much many of the Yang-Mills theories and other sort of generalizations of Maxwell's theories. And as I said, string-like excitations are in some ways the natural degrees of freedom to describe these theories with. And I think you should be able to develop the framework for describing the equations of these strings and thereby using it to compute, using it to calculationally predict things in the interactions in these strongly interacting systems, which you can't very easily do using conventional quantum field theory. So I feel that is an avenue where string theory can come up with predictions building on these new insights of the ADS-CFT correspondence. It can try to come up with new predictions for strongly interacting quantum field theories, which you are otherwise it's very difficult for you to do, simply because the usual quantum field theory picture is very difficult to tackle, whereas the string picture might be simpler to study. So this is the hope, and I think we are still some way from there. For that, we have to develop these equations governing these higher dimensional strings in a more precise way and applying it to broad generality. We seem to have this for many Yang-Mills theories, but we don't still understand how general it is and how to generally get the equations for these strings in this higher dimensional space-time. I think once we do that, I think we'll be in a very powerful situation to make predictions for interacting systems that are of interest to actually many physicists. So yeah, that was a bit of a long answer, but I hope I tried to convey it.
Thank you, sir. And Anand has another question. Anand, could you unmute?
Good evening, Professor. Thank you so much for the lecture. Like, really enjoyed it. I had a question about like the ADS CFT correspondence and like this holographic picture of space-time. So you had actually mentioned that like at least the example that you gave was of like QCD strings in 4 dimensions, like understanding that theory in terms of like 5 dimensions, like, you know, like strings without any thickness in 5-dimensional anti-de Sitter space. So is that actually just a mathematical convenience as in a way to understand like something in 4-dimensional space-time, or is it actually prescribing what the space-time is over here? I didn't quite get like.
Yeah, no, that's a very it's a very good question, very perceptive question. I think I would view it as a convenient way to view the equations. The 5-dimensional space-time is in some sense emergent. I think in ordinary Yang-Mills theory, you don't maybe that 5-dimensional. Well, it's a bit choice of the 5. If you wish to think in terms of a 5-dimensional space, that space is so small that you don't see the 5th dimension. It's sort of at the nuclear scale, and therefore you don't really see the additional dimension, and it's therefore not a real classical geometry. It's in some sense emergent. So the whole notion of space-time seems to be an emergent notion in that sense. So this is a particular case of an emergent space-time direction, this additional dimension. And it's in some sense a mathematical or an alternative mathematical way to describe it. Under some circumstances, one can imagine, but I don't think it would apply for QCD per se, but under some circumstances, one can imagine that this 5th dimension can be very large and it would be perceived then as an actual physical dimension. But and in which case you would view that description as more fundamental in some ways, but that's a different regime, but not the regime in which I think you would see QCD in QCD. So if you wish, you can take it at the moment as just a mathematical way of describing the equations of QCD.
Hello, sir. First of all, thanks for the amazing talk. There are two questions in the chat which are kind of related, so maybe I'll ask them together. The first question is this form of string theory in 5 dimensions different from the superstring theory? And
no, not really. I mean, I think the superstring theory is the one which is in some ways the consistent string theory, the only consistent string theory we really know of. And while it is often said to be in 10 dimensions, and that's depends on a little bit on certain assumptions. And in the simplest case of the ADS-CFT correspondence, there is actually a 10-dimensional spacetime of which there is a 5-dimensional piece, which is the anti-de Sitter spacetime that I mentioned. And then there is an extra 5-dimensional piece, which is like a 5-dimensional sphere. So it's a compact case, it's a kind of a sphere, so it's compact as opposed to the ADS space, which is like a non-compact or a infinitely extended space. So in some ways, the Yang-Mills theories effectively live in an effectively 5-dimensional spacetime. There might be some additional directions from the superstring which are needed for the underlying consistency of the superstring theory, but those don't play a very fundamental role in the equations that one needs to consider.
Anand, can you change?
Oh no, Professor, I just add a small clarification about your answer also. You said that we could consider that 5-dimensional space as being the real description of the space-time, but in this case it is anti-de Sitter space, and that isn't exactly what the universe is described by, right?
Right.
So yeah. I wanted a little clarification on that matter.
So that's why I said for the case of QCD and so on, it's not, I think, really the kind. It's a kind of a bit of a mathematical equivalent. It's more a way of writing the equations of QCD in a mathematical way. That space-time itself is probably very small and quantum at some level. So there's probably no sense of thinking of it as a geometric, very large spacetime to which Einstein's equations hold, etc. So that's why I think you shouldn't confuse that ADS spacetime with the spacetime of our universe. The universe, there may well be a picture for the entire 4-dimensional universe and any other dimensions that we have as also emergent from some underlying quantum mechanical system. And the spacetime is emergent in some limit when the distance is much bigger than the Planck scale. There may be such a picture for even flat spacetimes or de Sitter-like spacetimes that we are in, but we don't know those yet. We have a description of the emergent quantum spacetime when the spacetime is anti-de Sitter. And there are hints that there is a similar picture for flat spacetime and for de Sitter-like spacetimes, but that picture has been less fleshed out, in particular what kind of underlying quantum mechanical system would describe such a spacetime. So there are those puzzles are still not resolved. I mean, those puzzles, I think, are still there. So this is why I framed it frame the ADS safety correspondence more as a way to try to understand the dynamics of Yang-Mills theories and the strings of Yang-Mills theories.
Thank you, sir. There's one more question in the chat. It says, could you give a brief overview of how in the developing phases of the theory models were in multiple higher dimensions, but then brought down to 5 dimensions eventually? Could you give some intuition about this?
So the 5-dimensional picture, as I said, is part of the overall 10-dimensional picture of superstring theory. You do not have, in string theory, it is not necessary that all these dimensions be geometric and purely given by some space-time geometries. There are other ways of effectively having a 10-dimensional geometry, which effectively obeying the constraints that the 10-dimensional geometry has. The simplest way of realizing it was through a full-fledged 10-dimensional space-time, and people in the original days when they were describing string theory in flat space thought of string theory on ordinary flat space times some 6-dimensional internal space-time, which was very small, etc. But that's not the only solution of string theory. String theory allows for multiple solutions where you can have things which are 5-dimensional, and there's additional dimensions, sometimes fewer than 10, and those can be non-geometric also. So these are more complex solutions which I think people had not explored enough, and they or hadn't seen that they would be relevant to the describing our the kind of universe we are in. In particular, they hadn't realized that you could apply it to studying the equations for strings for Yang-Mills theory. So this is why these had not been looked at. But in recent years, people have realized that there are such solutions, and there are many of them in string theory, and they're worth looking at. They really expand our horizon of allowed sort of string theory solutions.
Thank you, sir. And maybe like one final question, and maybe Amulya, could you?
Thank you, sir, for this lecture. So I want to ask a question that is related to that strong field, sir, that quarks. So you said that quarks are confined because as we increase the distance between them, the force increases. So how we detect them? I mean, how we found them experimentally? If they cannot be separated, cannot come out of the protons and neutrons.
Yeah. So there are two ways. Historically, the way it was, the people convinced themselves that quarks are real objects is that inside the proton, actually, when they are very close to each other, the converse of the fact that their force between them increases as you separate them, the converse is that when they're actually very near each other, they feel no force. They're almost free when they are very close to each other, like inside a proton or inside a nucleus. So people actually bombarded nuclei, protons, with electrons, somewhat like the Rutherford experiment. In the Rutherford experiment, you were bombarding alpha particles of some nuclei, and you kind of detected the fact that there was a nucleus by the fact that some of them were deflected by 90 degrees or 180 degrees and so on. Some people did in some sense, much more energetic versions of Rutherford's experiment of bombarding electrons onto protons, and thereby probing the inside of the proton. And you could see that there are actually point-like structures inside the proton corresponding to the quarks. You could describe the experimental results by modeling the proton in terms of point-like structures inside the quark, inside the proton, and which behaved exactly like quarks are supposed to behave. So that's the historical way in which people became more and more convinced that the quarks inside are really obeying this. And then there were many other numerical works using very sophisticated supercomputers on computing the bound states of these quarks using the interactions of these Yang-Mills theories. You can only do it on very sophisticated supercomputers. And after many years, people actually were able to reproduce the spectrum that I mentioned of these bound states in mesons and so-called baryons using the underlying equations for quarks. So reproduce them fairly well. So that gave added confidence that this underlying quark picture was correct. But finally, in the last decade or so, people have been probing a phase of nuclear matter where the quarks can be deconfined. So this happens when, in a sense, the nuclear matter is heated to a very high temperature. So then they form a kind of a plasma, and the quarks actually can be deconfined. So when I said the quarks are confined, that's really only at zero temperature. But when you have, if you kind of make a plasma of nuclear matter, in principle, the quarks actually can be deconfined. And this deconfined phase of nuclear matter has been now detected in these relativistic heavy ion colliders, like the one in Brookhaven in the US and even in CERN and so on. And people have studied the properties of what is called the quark-gluon plasma that describes this, and really found evidence again for these quarks, but now in a kind of a plasma. It's like a bit like an electron plasma that you have when you ionize many electrons, many atomic systems, and ionize them. The electrons free themselves from the nuclei, and the whole thing forms a plasma. It's a bit like that. So here quarks and get liberated, and they form a kind of a plasma, and you can predict the quantitative properties of this plasma and experimentally try to verify them.
Thank you. Thanks again for the elaborate answer. And we're sure many of you have either follow-up questions or even more thought-provoking questions. So if you happen to have them, do mail us at our official email ID. I've just sent it in the chat. And so once again, do join me in thanking Professor Rajesh Gopakumar for delivering this fantastically structured session. So naturally extrapolating from the four fundamental forces and going all the way to quantum field theory and ending at string theory. And everything seemed to connect so very seamlessly, needless to say. And also appreciated was the fact that how mathematical techniques are used in physics and so many more thought-provoking questions. So thank you very much again, Professor Rajesh. And so we next meet on the next Saturday, which is 6th November at 7 p.m. IST, where Professor Saya Karmakar of the University of Florida will be giving a really curious talk titled Learning Dependence Independently. Hope to see you all there. And thank you very much, Professor Rajesh, once again.
Yeah, thank you, all of you, for organizing this very nice event and for all your very provocative and very thought-provoking questions. And I hope many of you will be enthused and continue to study more of this fascinating subject of string theory and maybe answer some of the questions that we still don't have answers to. So thank you and all the best. Bye.